Hello everyone, I hope you are doing well. In this video I'm going to talk about C++ asynchronous programming, models, patterns, libraries that has to do with asynchronous programming, and also the APIs or libraries that is going to be added in C++ standard STL library in the future and might be added also in the C++ 20. This video covers these three main parts: executors, and the second part will be about some example in Boost.Asio library, and also the final part will be about Libunifex library. Okay, I'm gonna explain executors with a very simple example. Here we have a simple hello world function. It just print out the hello world message, and in the next line we post the callable or invocable object to the executor or execution context through dispatch function. At this point, ex variable refers to an executor or execution context. An execution context could be a thread or a pool thread or anything that is able to run an invocable object. Okay, let's define executors more precisely. Executor is about set of rules about where, when, and how to run a callable. And a callable can be a function or function object or lambda function. What do we mean by these three words? Let's start with where. Where refers to internal or an external processor, or more precisely, it refers to execution context. It also could be, for example, a host machine, anything that is able to run an invocable object. What do we mean by when? When refers to the time that the invocable object is going to be run on execution context. A work is able to run immediately, or on a specified time, or after a delay on execution context. And the how part refers to CPU or a GPU context. Okay, let's see a simple example with executor and execution context. Here we have a bank account class, and bank account is an active object. If you're not familiar with active object pattern, you can find this design pattern on the Google. But I think this design pattern brought mostly from Java world. And bank account is an active object, but it's very simple. Actually, an active object is an asynchronous object. It means all the functions inside an active object is able to run asynchronously. It means an active object has its own thread, or more precisely, it has own execution context. Here, bank account has a thread pool. It's instantiated at this point, and it has two simple functions: deposit and withdraw. Deposit just adds up to the balance, and withdraw just decrement the balance. The operations are so simple, but the functions are not blocking. Actually, the increment or decrement operation will be posted to the executor or thread pool. Okay, this is an active object. It means through executor, an execution context, we can implement an active object very easily. As you have seen in the example, the thread pool was an example of an execution context. Actually, execution context refers to the place where function objects will be executed, and it's totally different from executor. Executor refers to a set of rules. Okay. But in this video we are not gonna cover those rules. You can find them inside Boost.Asio library or any library that is implements the executors. It might be HPX. I think executors also implement in HPX library. It's implemented in Libunifex, Boost.Asio. Yeah, and also I put a link at the end of this, I think in the middle of the presentation. I will show you the link. You can find just executors in a GitHub repository. Okay, usually in an active object pattern, we need to wait for asynchronous operation to be completed. There are different ways to do that. One of them is use the futures. Futures are proposed in C++ 17. They are asynchronous primitives, and you can find the documentation in C++ 17 about them. Okay, the post function is able to retrieve a third argument. If we pass this constant as third argument to the post function, then post function return a future, and through this future object we can wait for asynchronous operation to be completed, or get the result from the asynchronous operation. Here the template parameter is void because this operation doesn't return anything. The return type of this lambda function is void. That's why the template parameter of future is void. All right. There is another way to wait for asynchronous operation to be completed. It's just a simple function handler. You might have seen function handlers in POSIX socket API or any C network libraries or platform APIs. They are super simple. Here we have a redefined withdraw function. It takes a new second argument called token. Actually, tokens refers to the function handler. Here the type actually is a universal reference. If you're not familiar with universal reference, you can find universal. Actually, universal reference are introduced by Scott Meyers in Effective Modern C++ book, and the concepts are somehow simple. And the function handler is passed to the post function as third argument, and after running the function by execution context, the function handler will be run by execution context. Finally, okay, let's get into more in dispatch function and post function. Actually, dispatch or post function is able to retrieve multiple completion handlers, and the execution context will run the completion handlers in a consecutive way, one by one. And it passes the result from one completion handler to the other completion handler. Here we have passed 5 completion handler to dispatch function. The execution context will run the first completion handler at first, and then it will pass the return value to the next completion handler, and so on. And finally, it returns the final result through the future. It means at this point, this string will be printed. Okay, let's extend bank account class more. Let's say we are going to implement a new function in bank account class called transfer. In transfer function, we want to just transfer an amount of money to the target bank account in the second argument. The implementation is really simple. We just need to decrement an amount of money from current bank account and adds it up to the target bank account. But each bank account object is an active object. It means each of them has its own execution context. We need to run each operation on their own execution context. It means we need to decrement operation on the current bank account execution context, and we need to increment operation on the target bank account execution context. Okay, you have seen dispatch function and post functions signature. It retrieves it retrieves an executor or execution context as the first argument, but we can pass just completion handler to dispatch or post functions. But we can also connect each completion handler to a specified executor or execution context through wrap. Actually, we can wrap every Lambda function with an executor or execution context. Here we have used wrap function. We have wrapped this decrement operation with current executor in the current in the current bank account active object, and we have passed a second operation, actually a wrapped operation. It's the increment operation, incrementing the balance to the target bank account, and we wrap the increment operation with a new executor, and the executor it refers to the target bank account executor. And finally, we have passed the token or completion handler. You see, actually, executor and execution context makes the asynchronous life very easy. Here, we post two asynchronous operations to two different execution contexts without having any synchronization primitives or other object that has to do with asynchronous API. Okay, I brought these examples from this library, but these executor and execution contexts are also implemented in Boost.Asio library, and it was intensively used in network programming. Okay, in the second part, I'm going to get into some examples from Boost.Asio library. Here, it's a simple example. It's an echo server that is implemented by Boost.Asio library. In the first line, we have an execution context object. The I/O context is an execution context for I/O operations. It's implemented by Boost. And in the second line, we have an I/O object. It's a TCP socket, and we bind it to this execution context. It means this I/O object uses this execution context for all its asynchronous operation. It means all the asynchronous operations will be run on this execution context. But this execution context is not a thread or thread pool. You will see how can we bind this execution context with a thread pool. Okay, and here we have three functions. In a start function, we initiate an asynchronous read operation to this I/O object, to the socket, and it also gets a completion handler, and this is the completion handler. Actually, it's somehow same as the executor, same as the posting a function to an executor, but here we have a specified operation. The operation is asynchronous read. Okay, and the completion handler, but this is just a lazy work. It means when we call this function, it does nothing. It just initiates an asynchronous operation to the execution context. Okay, when this operation is run by execution context and it's completed, then the completion handler will run. It means the handle read function will be run after this read operation. And in handle read function, we initiate another asynchronous operation. It's an asynchronous write operation on this I/O object. And we also passed another completion handler. It's handle write. And after asynchronous write, this function will be run. And then we initiate an asynchronous read operation again. It's somehow same as a loop, but it's not a loop. It's actually a chaining of call, and also it's not a recursive call. It's chaining of call. We initiate another call after one call. Okay, we just when we run a start function, we just initiate a lazy work or initiate an asynchronous operation. It means it does nothing. When we fire the IO context or execution context, then the program starts to work. How can we do that? The IO context has a function called run. As soon as the run function is run, then the program starts to work. We can call this function on a thread or a thread pool. Okay, coroutine is another asynchronous concept in C++20. I'm not going to get into the coroutines details and also the coroutine objects. You can find them in C++20. Okay, here this is the echo server that you have seen in the previous example, but it's implemented by coroutines. Boost.Asio library also supports coroutines, and it's also implemented coroutine objects. Okay, echo function retrieves the IO object and also a coroutine execution context. And here we have the loop. In the loop, we just read from the socket and write it back to the socket. It's super simple. At this line, we initiate an asynchronous operation to this execution context, and when we pass a coroutine execution context to the Boost library functions, it returns an awaitable object, and then we can use co-await on an awaitable object in order to wait for this operation. When this task is run, it returns, and in the next line we initiate another asynchronous operation. This is an asynchronous write on this IO object, and we passed a coroutine execution context, and it also returns an awaitable object, and then we wait for the completion with co-await function. Really simple and readable. In the third part, I'm going to talk about Libunifex library. Unifex stands for Unified Executor. This library is implemented by Facebook. You have seen some examples from executors and execution context. Executors are really perfect to solve actually asynchronous problems, but they are not enough. For example, if we want to chain or compose different asynchronous operations, and if we want to have cancel operations or stop operations, it's somehow difficult or impossible to implement it through just executor and execution context. We do need more generic algorithms in order to compose and chaining the different asynchronous operations and making new composed asynchronous operations. It might be possible in Boost.Asio library to chain some different asynchronous operations, but it's so limited. Okay, actually, the one of goal of Libunifex library is to implement these generic algorithms in order to compose different asynchronous operations and make more complex asynchronous operations. In Libunifex library, a new programming model is introduced called sender and receiver. And in this programming model, there are some concepts that we are going to define them. There are four main concepts: sender, receiver, scheduler, and operation state. Senders refers to the lazy work that is going to be scheduled or posted on the execution context. sender can bind with a lambda function or a function, but the sender is not going to return the result. It's going to send the result to the receiver. It is able to send the result, or send the error to the receiver. And receiver refers to the callback. Actually refers the callback. Receiver is a callback object in order to receive the result from the sender object. And we have another concept called scheduler. Scheduler is exactly same as execution context that we have in Executor, but here it's introduced with another term, scheduler. And in order to run an asynchronous operation, every sender should connect with a receiver. And when we connect a sender to a receiver, the result will be an operation state. It means operation state at least refers to a simple sender and receiver connection. Okay, let's see a simple example. In the first line, we have an object from an execution context. This is a single thread context. In Libunifex library, executors and also execution contexts are implemented. And here we get the scheduler, or somehow we get the executor from the execution context. And also here we have a lambda function. We post this lambda function to this scheduler in order to run on that. And we have done that through calling execute function. Execute is somehow same as post or dispatch function in executor library. Okay, let's see a simple example from senders and receiver. In Libunifex library, senders and receivers should have a specified interface. Every receiver object should implement these three functions: set value, set done, and set error. And as I said that earlier, every sender is connected to a receiver, and when the work is done on sender, the sender will call one of these functions. If the sender calls set value function, it means the work or sender is done successfully. If the sender calls set done, it means the work is cancelled. And if the set error is called, it means sender is not completed successfully and it gets an error. And here we have two receiver, my receive 0 and my receive. And in my receive 0 set value function, we print out impulse, and here we print out the value. Okay, at this point, we declared execution context. It's a thread pool called pool. We get the scheduler. In Libunifex library, in order to compose the asynchronous operation, we need to convert them to senders. Actually, we are able to compose or chain the senders. Senders somehow are our main concepts. Here, we turned the scheduler to a sender. It's called a single shot sender because there is no work on these senders. The sender is just it just calls the receiver immediately. I mean set value function. Okay, here we have a sender. It's a single shot sender. And as I said that earlier, we need to connect a sender to a receiver. We can do it through connect function. We pass a sender and an object from a receiver, my receive 0. And the connection returned an operation state. And the operation state refers to the senders and receiver, or more precisely to the lazy work. But it does nothing. In order to start the program, we need to run the operation state. We can do it through calling a start function and pass it the operation state. Okay, that's it. And this single shot sender, when this single shot sender is run, it just immediately call the set value function on the receiver, and that will print the impulse. Okay, there is another example. This is a simple function. It receives a value and it multiplies by this double value. And there is another function, print. It prints out the double. And here we have composed three asynchronous operations, or three asynchronous senders. We have used the function from Libunifex library. Just generates a new sender, and this sender just generates a value. And here is 2. And in the next line, we have another function from Libunifex, on. It also generates a sender, but this sender causes the chain or the composed operation to run on a specified scheduler. On the next line, we have another function. It also generates a sender. It gets a function and it generates a sender. And this sender causes to transform the value on the lazy work or on the sender. Okay, and we have changed these three senders by these pipe operations, and the result will be a new sender. Okay, but and this sender refers to a lazy work. It does nothing. If we want to run this sender, we need to connect it to a receiver and then start the operation state. We can do it through submit function. Submit function receives a sender and a receiver, and it starts the sender to work. Actually, submit function connect the sender to the receiver and then start the operation state. Okay, it was about sender and receiver. Let's see another example. Actually, in asynchronous problem, this is a common pattern that we usually need to chain or compose different asynchronous operations, and when all the asynchronous operation is done, we need to propagate the result or reduce result, or sometimes if one of those asynchronous operations deals with any error, we need to stop other asynchronous operations and propagate the error. This is one common pattern in asynchronous programming. And we can actually achieve to this common pattern through when all function from Libunifex library. I would say that it's one of most useful function from Libunifex. It receives multiple senders. Senders are lazy work, and it generates a new sender. Okay, let's explain this program, this simple snippet code. Here we have an execution context. This is a single thread context, and we get the scheduler at this point, and here we have actually a composition of some asynchronous works. Okay, let's start from the inside. Then function, actually it's also a sender generator function. It receives a sender and a lambda function. Here, schedule after generates a sender, and actually it somehow schedule a single shot sender on a specified time, and it generates a sender. Then receives a sender as the first argument, and it receives a lambda function as a second argument. It generates also a new sender, a lazy work. But what does the sender? The sender will run this function after this sender. Okay, and here when all function gets two senders. Two senders that is generated by then. And when all also generates a new sender, returns a new sender. And we have passed the sender to the then function, Second argument of then function will be a lambda function. It will run this lambda function after this sender. Okay, and the result will be just a simple sender. We can run this sender through calling sync_wait. Sync_wait is same as submit function that you have seen in the previous slide. Okay, let's get into another example. Here we also used when all function. When all is really one of the most useful functions in Libunifex library, and it's really awesome. Just to mention something, you see we composed 3 different asynchronous operations, and the code is really clean, and we wait for all of these asynchronous operations and we get the result without any actually synchronization primitive and any knowledge of threading model, I don't know, atomic or memory order and this kind of stuff. And this is the main actually benefit that's brought by Libunifex library, and it's really awesome. Okay, here we have another example from when all function. It's really useful, and the senders are generated by the make thread task. Here we have another execution context, new thread context. Actually, new thread context is an execution context that generates new thread per scheduler. It means whenever we call the get scheduler, it generates a new thread. Here in make thread task, we have then function, and we have passed the sender to the then, and we have passed a lambda function as a second argument. And we call the make thread task 4 times in when all function. It means it generates 4 different tasks with 4 different threads. And when all function will wait for all of these asynchronous tasks. When all generates a new sender that refers to these 4 composite asynchronous operations, and finally we wait for the sender to sync_wait function. Okay, here you see a similar example, but we wrap. You see, this is a common pattern that's usually used in Libunifex library. I mean, then and passing a lambda function, because if we want to run a lambda function on a specified scheduler or on a specified execution context, we can call then function in this way. We can wrap these 2 functions in a new function called run on. We use then inside run on, and we pass the scheduler with a specified execution context, and we have passed the function as a second argument. And this is actually same as the previous example. We just passed 3 senders to the when all function, and it generates a new sender, and finally we wait for the sender to sync_wait function. Okay, let's see another example. There are different classes and facilities inside Libunifex library. For example, one of useful classes in Libunifex library is about ranges or streams. Ranges or streams in Libunifex library are lazy containers. Okay. It means the values in the container will be generated lazily. Here we have an execution context, and then at this point we generate a stream of value through range stream class from Libunifex library, and we want to generate this stream on a specified scheduler. We can do it through onStream function. onStream function get a scheduler and a stream, and it will generate this stream on this specified scheduler. Okay. And the onStream result, I mean the returned will be a new stream, if I'm not mistaken, or a new sender. But it doesn't matter. It's self-explanatory. I don't want to get into the types that is returned by these functions. Most of the functions will return the senders, but some of them also just return a transformed stream or something like that. And we piped this stream, the result stream, to a for each function. This is also a lazy task. Actually, it gets a lambda function, and this lambda function will apply on each value of the stream. And then we piped the result to another sender. Stop when is another function, and it will generate a new sender. And it stopped the sender after a specified time. Okay, the result will be a sender. And we want to run this sender on a specified scheduler. We can do that through on function. The on function gets a scheduler, and also it gets an operation state. Sender. And this sender will be run on this specified scheduler. Okay, that's it. And I think this is the final example. No, we have also another example. Here, this is another example. Let's start from the inside. We have generated a stream through range stream, and then we transform the stream to another stream through transform stream, and this is the transform function. It means this stream will be transformed by this function, and the result of transform stream will be a new stream. And then we bind the transformed stream to a for each. It means all the values will be passed to this for each function or processed by this function, and the result of for each will be a sender. Then sender passed to the den. As I said that earlier, then gets a sender as the first argument, and it gets a lambda function as the second argument. This lambda function will be run after the sender. And finally, the result will be a sender, and we run this sender through sync wait function. Okay, another example. Here we also have a stream. Let's explain from the inside. Here there is a stream. It's generated by range stream, and there is another stream related function called delay. It causes to generate a stream values by an specified delay. The delay function receives a stream and a scheduler and a specified delay, and it returns a sender or a stream. I don't know exactly, but these stream values will be generated lazily. It means each value will be generated after 100 milliseconds. Then we passed the stream or sender to the for each, and every lazy value in the stream will pass to this lambda function one by one after 100 milliseconds. The for each will return a sender, and and sender passed to a stop when function. Okay, a stop when function causes to stop a sender. It receives a sender as the first argument. It stops the first sender when this sender will run. Actually, it receives two sender. it will stop the first sender after the second sender. Okay, in the second sender, we use then function, and then function scheduled this task on a specified execution context after 500 milliseconds. It means this lazy stream will run, and after 500 milliseconds, the work will be cancelled by this scheduler. That is really awesome. Okay, I think this is the final example. Here we have another stream, and then we transform the stream. We transform a stream function, and this is the transform function. And finally, sorry, it's not final step. And then we reduce the stream by the reduce stream function. It means the reduce function gets a stream and it generates a new stream. And this reduces stream. This is the initial value of reduce function, reduce functionality, and this is the reduce function, and it somehow is like an accumulation. It accumulates all the values on the stream, and the result return to then function, and then function. Okay, it means reduce a stream returns a sender. Yeah, it's a sender. A sender passed to the then function, and second argument is a lambda function. It means this lambda function will run after this sender. Okay. And I think I forgot to mention it. Then function receive the result from the sender, and it passes the result to the second argument, to the lambda function. It means the reduced result will be passed to the lambda function, and here it sets to the final result function, and finally it prints out the final result. It will be the accumulation of this stream. Okay, that's it. Thank you so much for watching us, and see you later.